This is the 39th lecture in a series on single agent search. And today we're going to be looking at what happens when we try to apply constraints into search. And particularly in this video and the next video, we'll be looking at what we would call a canonical ordering, which really is very related to the types of constraints we've applied in other domains. And so we'll have two videos on that. In the second video, we'll be getting algorithms. This video is mostly going to be giving background. And jump point search is one of the most well-known algorithms we'll be covering in the next piece. So we're going to get to canonical orderings. And so if we look at this topic here, what we might look at is we think about Rubik's Cube. And in Rubik's Cube, what did we do? So Rubik's Cube, we started out with there are 6 possible edges or 6 faces that could be turned, and there's 3 moves each. And so this gives us a branching factor of 18. But we saw in practice that by having a first and second face, that we can get the branching down to just a little bit over 13. And so we'd like to say, this is a really good idea. It works in Rubik's Cube. And if we think about something like the sliding tile puzzle, we avoid going to our parents. There are more complicated rules that could be done there. So there's some older work that looked at how you could use finite state machines for pruning there. And there's a very general work that's been done, was published at the SOX conference by Neil Birch and Rob Holte about how to also do pruning. And then when you get into planning, there's actually quite a lot of work in planning that looks at how we can avoid having duplicate states and regenerating states that we don't want. And so the question is, how can we apply these not from a domain, for instance, like the Rubik's Cube, where either I can analyze it, but the Rubik's Cube is what's called a Cayley graph. Everything looks the same in every direction. And so if we look at Rubik's Cube, we sort of can see, well, maybe I can come up with some rules because the state space is so uniform. But what if I go to a grid map and think about in a game? And when I do that, what can happen there is that basically, well, I've got all these, my map is not necessarily uniform, but I can have a map with obstacles in it, and it could be very non-uniform. So we'd like to come up with some ways to figure out how to do some pruning and remove some of the duplicates. And we're going to give a spectrum of different algorithms that we can do for this in the next lecture, as the next video. But as I said here, we're going to build up the foundation. And so here, what I want to start at is by looking at a picture here. And so we look at a picture of a map with the start in the lower left and the goal in the upper right. And let's just assume for right now that the map is totally open. Then what you would see is within this map, if we ask the question, for instance, where are the possible optimal paths that we could follow? Basically, everywhere in this region is part of an optimal path. Okay, these are all different paths that we could take that would be coming here, coming here, and then coming here. Or I could choose to go here, to go here, to go here. And what you can see is that there might be, and there are in fact many, many different paths we can take. And we can think about how many possible paths there are. If we say that this length right here is m, and this length here in terms of the number of edges is n, the idea is that the path length, here we're thinking about an 8-connected grid, so we can either go in cardinal or diagonal directions. The total length of the path is m plus n. We're going to take m steps. Basically, we have to take m steps going this way. We have to take n steps to go that way, and eventually we will reach the goal. There could even be obstacles in here that we have to go around so that maybe there aren't the path would still be m plus n, but maybe there aren't all possible paths we can do in between here. But let's look at what happens. So if I have m plus n as the length of my path, then the idea is at some point in this path, I'm going to have to distribute n actions, which are my moving up actions, and the rest of them will be my moving right actions, or sort of moving diagonally up. And this generalizes, sort of as you go around a quadrant. Here we're going to assume that m is greater than n. And so, and in fact, it actually doesn't matter the way the formula works out, but basically what we have is we have m plus n is the length of my path, and then I'm choosing from that n possible ways to distribute my up actions. Okay, And so this is looking at m plus n factorial over m factorial and n factorial. So what we see here is this exponential growth of the number of possible paths that we can take through even a simple grid like this. Now we have this property in the cost space that we have here that says when I arrive at a particular state, it doesn't matter the path that I got there. All that matters is the cost of arriving at that state. And if we have that assumption, which we generally do for many domains, one notable example for this would be DNA alignment. There are cost functions in DNA alignment that don't have this property. And so if we do have this property, though, then although there may be an exponential number of paths to get to any particular point, what we can discover is basically that we don't have to look at all exponential numbers, something like dynamic programming, because I know once I've reached a particular state, I actually can say I'm done with the history. And so in that way, I can just go through here and look at every state once, for instance, with Dijkstra's algorithm. Okay, so there's an exponential number of paths. In practice, we only need to look at, and this number would be sort of the number of states there are, not the number of paths, which is good. But there would still be some advantage in, for instance, how many duplicates do I have to look up, or how much processing do I do when I'm thinking about this general piece. And so we're going to take a look at this, and what we're going to define next is the idea. So this is just showing us how many paths there are. We can now talk about a canonical ordering. And a canonical ordering is basically says, look, from one set of paths, so like this set of paths here, what we're going to do is we're going to say, of all these paths which are equivalent in length and move through this space, there's some formality here I'm going to gloss over about maybe having two very different paths that go to the goal in different ways. But if I think about a space like this and I ask, well, what of all those paths, what can I do? Or how could I order them? Or how could I say, like, I prefer one path over the other? So canonical ordering is a way of basically saying I have a preference of which path I like. And we can think about saying, well, enumerate all paths, and then I'm going to tell you one of those is the canonical path. And so what we're going to say is the canonical path if we think about between P1 and P2, so we're going to think about, just again, I'll draw a simple example here. So P1 is going to go diagonal and then cardinal. P2 is going to go cardinal and then diagonal. And what we're going to say is that if we're measuring the cardinality, it's basically a relation between paths. And we're going to say that we prefer P1 is preferred over P2 because the diagonals are before the cardinals. Okay, what that means is that in P1, they both get to the same goal, but in P1, the diagonals are first and the cardinals are second. In P2, the cardinal actions, cardinal meaning north, south, east, west, are before the diagonal actions. And so what I prefer is P1 over P2. There's another path here that has like a cardinal and then a diagonal and then a cardinal and a diagonal. So this path, if it was P3, would be preferred over P2 because it has some diagonals before P2. But in terms of like the maximum relationship, so if we were to be, write this as being greater, or you could write it as being less, but we're thinking about the maximal relationship in terms of what is the best canonical path. P1 would be the best possible canonical path because all of the diagonals are before all of the cardinal actions. So this is a way we can compare two paths, and we can think about which path is preferred over the other path. Okay, so that gets us so this is what a canonical ordering would be from all these sets of different paths. I'm going to choose an ordering of operators, the canonical ordering of operators, which meets some criteria which we're going to define in a maximal way or minimal way, something like this, in some relation. Okay, and so in this case, we're saying we want diagonal actions before cardinal actions, but there's nothing, set in gold about that. It could be, or set in stone, sorry, it could be that we wanted to do cardinal actions before diagonal actions. It could even be, say, we're going to go up right before, going up left or something like this. We really just, we set any precedence on the operators, for instance, and then just say, the canonical path is the one that follows that precedence of operators. Okay. And if we do that, then we can start to think about a canonical ordering. And if in particular, if I can actually, given a start state of a map, I can start to think about different paths that I can take. And the way that I like to teach this is through a few different steps. So we're going to think about a basic canonical ordering, and we're going to do an example in just a second. I will put a link down below, and so I'm going to do a basic overview here. And then I will encourage you to go look at the example and try to do this yourself, and then I'll go through the example. Okay, so the idea here is we could have some map, and I'll draw a somewhat abstract map here. Or I'm just going to draw a little piece of it. So what I have here, for instance, is I have, for instance, an obstacle. And maybe I have another obstacle here. And the idea here is what I want to think about is how do I actually write down or think about what is the canonical ordering on this particular map. I'll move that down slightly. I'll move it over slightly just to make it clear where the grid sort of lies underneath that. So a canonical ordering would basically say, look, imagine that I'm at the start. And for right now, all I'm going to be able to do when I'm at the start is that all I'm going to be able to do is get on my basic canonical ordering, it'll get me to the places that are immediately visible from the start location. So for instance, if I want to get to the goal, because I want to take diagonals before cardinals, but there's no diagonal actions to get there, if I want to get to the goal, then I'm just going to go straight across to the goal. Or to if that was the goal. If the state below this was where I wanted to go, then remember the canonical path is going to take diagonal actions and then cardinal actions. So we're going to take a diagonal action first, and then take a cardinal action. And then similarly, the only other places that I can reach in direct visibility would be to go straight down. So this is what I'd call a basic canonical ordering. And it basically just says, look, starting from the start state, if you want to think about where you can get in the map, then these are the places that I can get, and these are the places that I can get sort of moving directly through free space. And in getting these locations, I get there optimally, and I'm following the canonical path. Now, what goes on here is if I want to get to the rest of the map, though, there's a problem. And this is actually probably the best insight. And to say that we're going to build up the jump point search, which is an algorithm by Daniel Harbour. And quite a number of years ago, he was working on just sort of symmetries in general. And then the symmetries expanded out to this final algorithm, jump point search, which will be in the next video. But what I'm going to show you here is really the key insight of what is done there. Because if we think about what happens in something like the Rubik's Cube, we just write down this rule, and then we know that we can still reach every state in the state space. But if I write down this rule right here that basically says diagonal and then cardinal, well, there's most of the state space here I can't actually get to yet. Because, well, you can see just in canonical paths, they don't take me there. And so the key insight, which allowed progress forward in this area, is the idea of what he called jump points. And jump points are simply points where the canonical ordering needs to be reset. These are points where there's a state that we know is not reachable by the canonical ordering is seen, and so we need to say that we need to go reach that point. And so in this map, there's two jump points, as I said, places where the canonical ordering has to start over. And they come at the corner of obstacles, and they only come at the corner of obstacles. So when we're going straight down here, this corner of the obstacle, so it's this corner of this obstacle right here, what we see is that as I was coming down in this direction, I can notice that on the side here, I would normally expect the canonical ordering to go diagonally and down. And so I would normally not have to generate any states along here as I was coming along here. But when I look at this problem, I see, there is an obstacle right here. And because there's an obstacle, then when I get on the other side of the obstacle right here, there are potentially states here that could not be reached because they were blocked. The canonical ordering was blocked by this obstacle. So what is happening at this point is that we now are paying attention to our environment. Our canonical ordering is not just a very simple set of rules, like, given this state, generate this state, but we're actually going to be looking at the environment. So for instance, in Rubik's Cube, we said if I've done a first face, and then I can do a second face, but then I can't go back to a first face. Okay, sorry, some technical issues there, and let's continue where we left off on this example. So we were looking at this problem here, and we've seen here that we can detect that the automated rules that we had, like we have for something like Rubik's Cube, are suddenly not going to be able to reach a state here in the state space, and they're not able to reach states here. And so the idea of jump points is basically we're going to restart the canonical ordering. And I'm going to just use a different color here to illustrate what's going on. So we restart the canonical ordering, and then we're going to think here about going out. And how do we reach states? By taking first diagonal actions, then cardinal actions. Now from the state here, there are no diagonal actions, so we would just continue to take cardinal actions. From the state here, on this side, we can take both diagonal and cardinal actions, so we would come this way, and we would come this way, and we would come this way in the state space. And then we'd also notice here, moving to another color, that now we have new jump points that are here. These are places where the canonical ordering is unable to reach. And in particular, what's going on here is that as we're scanning along here, what we're doing is we're looking if there is an obstacle and that obstacle ends in the direction of, that we're moving here, then we would see that there is no canonical ordering earlier here that could have taken a diagonal and then cardinal action to reach here. And so at this point, then we would continue with diagonal actions and cardinal actions. And the same thing here is we would continue with diagonal actions and cardinal actions coming off of those. And the last one would allow us to come and get around here. Okay, so what is the canonical ordering? The canonical ordering is a way of ordering the paths so that we take, in this case, we're going to take diagonal actions before cardinal actions, but in general, we could have some function that tells us the preference and we want to return those. With this particular ordering that we're going to use diagonals before cardinals, the nice thing that we get here is that we, instead of generating all paths, comparing them and selecting the canonical path, what we're able to do is we're able to just immediately generate the canonical path and use that directly. And so this gives us our canonical ordering. And what we're going to do now is a little exercise. And as I said a minute ago, I will make sure there's a link to the PDF document that you can use. But here is an example of a map. And let's just say that for a number of years when I taught this material, or several times when I taught this material in the past, then I thought students understood what was going on. And then I started using this map example and I discovered they didn't always understand it as well as they thought they did, or as I thought they did. And so what I encourage you to do is to take the link to the map that should look something like this. There's one big obstacle here. And go ahead and download that, put it on your computer or print it out. And given the start state that's sitting right here in the map, to go ahead and draw out what the canonical ordering looks like and where the jump points are in this particular map. So I encourage you to do that. I will give just a second here. You can obviously pause this video and then continue to do that. And then I will draw out much of the canonical ordering here. Okay, I assumed that you paused the video and went and did that. If you didn't, of course, then you might miss out on a learning opportunity, but at this point, that's on you. So let's see what we can do here. So I will use blue to go through here. So the idea here is we want to think, if I pick any particular state in the state space, and so I'll just do this for a couple states, we want to ask the question, what is the canonical path to get here? And that is the path that has, so I'm just going to choose a state down here. We can think about there are many paths to get here, and the easiest path, we might think the easiest path is something like this, but this would not be the canonical path because we have not put our diagonal actions before our cardinal actions. And so we don't want to consider this path as the canonical path. And the canonical path is basically going to be the one that goes diagonally. Let's see if I can get this directly through here. Diagonally, 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 diagonally. Notice on this map, I'm actually sitting in the centers of these locations. I'm not going, my agents are assumed to have some volume and sit at the center of a grid cell. Then we're going to go across here. At the first point where I can possibly do it, we're again going to go diagonally down. And then at the first point when I can do it, we're going to go across and diagonally down. And then we'll come to here. So this is the canonical path from the start to this particular state right here. And I actually should just continue this across here. And then we think about, okay, so what's happening when I get to one of these jump points? This is a jump point. I'm going to reset my canonical ordering. I'm only going to reset it in the direction of the obstacle. So the obstacle's here. I'm going to reset it in this direction. Basically, I'm going to add these two directions to my ordering, which means that I'm going to get a path right here. And similarly, on this next jump point, I'm going to get a path that goes here. My diagonal is going to continue right here. To get to this location, I would go diagonally and then down. And here I'm going to go diagonally and then across. Okay. So in general, the best way to draw out a canonical ordering is to draw your diagonal lines. From your diagonal lines, so one of the things people sometimes do is they'll draw a line like this coming from it. This is not correct because this doesn't actually give us the shortest paths. But what we want to do is something like this. We'd be continuing in this direction. And on the bottom side of this, then we're going to be coming out in the other direction here. And I'm going to turn my screen around, but you won't see this on the actual screen here. Let's go diagonally down here. And we get here. So now from each of these, we'll just continue to have cells here. This is actually, this is not a jump point. It may look like a jump point, but a jump point is actually when we're blocked. And here we're not blocked. And so we'll just continue to go down here. And then here, this is a jump point because we were prevented from going diagonally. So now we get this movement down here. We have a jump point here where we're going to start going diagonally again and then cardinally. And then on the other side of this line, we'll continue to go down in this direction. And I won't draw the rest of those out. If we look up here, we'll find some other interesting cases. So we can see that this point here, a jump point is always sort of next to an obstacle. So we have an obstacle right here. The ordering is going across here. And so we see that in practically speaking, would have normally come diagonally and gone up here. But because there's an obstacle, we're prevented from doing that, which says right here, we'll need to restart the canonical ordering. We'll come down here and continue. And one of the more interesting places to look at on this particular map is what happens up here. So I come here, this is going to be a jump point where I restart the canonical ordering, allowing myself to go down and diagonally here. And so we'll continue there, we continue across here. At this point, we're moving across here and we get another jump point, which is going to take us in this direction. And we'll also continue in the diagonal direction here. And the other thing that we see around this obstacle is that we'll have another jump point on this side. And this particular jump point is going to push us off into this direction. And we'll see each of these coming through here. We see these pieces going off here. And this is a jump point here. So, and this is a jump point here. Now, what's interesting here is that, so this jump point will continue us off in this direction. And what we'll see here actually, and let me just draw this in red to make it a little bit more clear, is that this line right here is also going to start to generate paths going this way. And it will, for instance, give us a jump point on this side of the obstacle. So what we can see here is that there are points like this. So this is not a jump point, but this is just where we're changing directions. But this point here is a jump point when we come this direction, but it's not a jump point when we come this direction. So one thing that says is that depending on how I generate my map, I may or may not generate duplicate jump points. And so that's something to notice and pay attention to. We'll come back to that when we think about the algorithms based around here. And then we see that coming in this direction, this is a jump point, the red point here. But when we come in this direction, it is not. So what's happened in this space is there are two possible paths to get here that would be canonical, not with respect to the shortest path, but if we just think about like the path to get here, there is a canonical path in this direction, and there is a canonical path in this direction. And so what that says is that we can't just use this canonical path algorithm of generating paths and jump points and things like this to immediately go out and search the entire state space and just find, like, go towards the goal and just find the shortest path in one step. It's actually a much more complicated problem than that. And so we're actually going to need a search algorithm on top of a canonical ordering. So what a canonical ordering does is it gives us a structure, something like here, that says, look, when I'm going in this particular direction, I don't have to look for obstacles on either side of the place where or I don't have to generate nodes in the open list. I don't have to look them up. There's a lot of work I would normally be doing on the neighbors of a state in the open list, thinking about all the states that are on the side here. And we can avoid doing that with a canonical ordering because we actually know, like, this is the path that I'm going to use to get here. But it doesn't mean that I just get optimal paths. I have no idea from the canonical ordering which way is the correct way to go around this particular obstacle. So we need a search algorithm to do that for us. And so that's going to be the subject of the next video. But I did want to show here just the picture of the final canonical ordering for this particular problem. So we can go look at this. So this is the complete canonical ordering that's been done out algorithmically here as opposed to mine. You can see the jump points have been marked with the circles. And then the paths are going out from there. And then in the upper left-hand corner, I've marked in red, or we've drawn in red. This is generated automatically. And actually, there is an online demo. So I'll give a link to the online demo that'll allow you to play with the canonical ordering, move the mouse around, or move the start state around and see what the canonical ordering looks like for different start points. But this is the beginning of what we're now going to get. So what is this giving us? Let's just talk about, we're going to get to algorithms the next time. But what this is giving us is it's actually starting to introduce constraints into our search. So previously we introduced constraints into our search by saying, for instance, you're constrained to not go back to your parent in the middle of search. The way that we introduced a constraint is we said, okay, in Rubik's Cube, you have a first face and a second face. And if you've done a second face, you can't go back. You're constrained. So constraints are about removing actions from the state space. And what we see here is our canonical ordering is removing actions. When I get to a particular state here, sorry, let me go back to my drawing of this. So when I get to some particular state here, I'm constrained and I don't generate the actions. In fact, I don't generate most of the actions. Right here, I'm actually only going to generate one action. I'm constrained to only go in a single direction instead of going in 8 possible directions. So this is the first introduction to constraints, and they're, or sort of a more formal look at what constraints are doing. They are bringing down the branching factor because they're marking some states as being illegal states in the world. And so we're going to see how we can use those not only in the next video, but in the videos after that. We'll be looking at different types of constraints and how those are powerful for improving search and speeding up search. And so come back in the next lecture and we'll look at algorithms that can be built using canonical orderings. We're going to build up a number of those. So we'll see you in that lecture.